Oh, good. Okay.
First speaker of the afternoon session is the Kazuo Tsushima. He's going to talk about immediate properties of low-lying bottom baryons in the key MC model.
Okay. Then gradually I start, and this purpose is to discuss, and I want to ask your opinions and also discussion questions. That is better. And the title is Immediate Properties of the Low-lying Bottom Baryons, but actually hyperons, strange baryons, charm baryons, everything is included. And this talk is interesting results is for Lorentz scalar mass of sigma B and cascade B. That is focus. But this is a phenomenological model, but finite density cases. So usually finite density QCD's application, direct application is difficult. This is phenomenological, but a little bit suggestive for experimenters. So before starting about the QMC model, Quark meson coupling model, I had many people who worked together and want to mention. Okay. Here, the screen. So this model's development and phenomenology, there are many people's contribution here. Okay, Gaston, of course, he recently wrote with us review papers and very nice paper, and also many colleagues, my colleague Pacheco and Amaro, Gilberto. And one thing, today archive our paper appeared on in medium electromagnetic properties, form factors. So please, okay, our group, small group in Brazil, but we are working very well. So I started to talk. Here. And, okay, first screen. Okay. So this topic is, as I mentioned, Lorentz scalar mass, because in Dirac equation for baryon, it appears, there appears Lorentz scalar and Lorentz vector potential, the so-called. This interesting result is for Lorentz scalar mass. And the talk is mainly based on this, and review papers, these two review papers, it's very useful, I think, and you will see applicability of the model. Then, okay, just. So second motivation is to make propaganda of our work and model. And one is also, okay, I want to ask the opinions from experimenters if something is possible. And okay. Especially recently, Quarkonia nuclear bindings, it's interesting because J psi and eta C bindings, nucleus, that potential is calculated, and also energy levels calculated, especially as new approach. Okay. First, I will talk about other motivations and the introduction. Quark meson coupling model and results for low-lying strange charm bottom baryons. Low-lying means at least one light quarks they include. Otherwise, not interesting because light quarks, quark condensates are very sensitive to the nuclear density. Then dynamical symmetry breaking or chiral symmetry breaking is related with the quark condensate. Quark condensates are order parameter. So that's why focusing on the low-lying strange charm bottom baryons which contain at least one light quark, and summary and perspective. Then, okay. By this study, in my mind, I think I completed the immediate properties of the low-lying strange, octet baryons, and charm sector and bottom baryons. So I can compare those three different sectors. In the Quark meson coupling model in finite density, but if some other models can do, I hope, for example, NGL model or NAM-Jonara model, it is also okay. But first they must solve Faddeev equation, some complexibility come out, so a little bit difficult. First, strange sector, hyperon sector, also NGL model, some people have done, but probably still it takes time, charm and bottom sector. And then I can compare strange sector, charm sector, and bottom sector. And okay. Because I just calculated, but I don't have so much idea. This result can be applied for some experimental checks. That is what I want to ask. And highlight is, I repeat, here some people can understand. For example, sigma B is two light quarks and B quark. Cascade B is light quark and strange and B quark. Then quark condensate idea. Here, two light quark condensate. They are influenced. But strange in the bottom here, cascade B, they are less sensitive. Then, although if you look at the particle data table, in vacuum, in free space, sigma B is heavier than the cascade B. That was surprising. I thought the cascade B is much heavier. But this non-relativistically probably color interaction gives, but it's, I don't know, it's real nature. But
what you call a scalar Lorentz mass is the same as effective mass?
This case is yes. Because in spin 1/2 baryon Dirac equation, there are Dirac Lorentz scalar part proportional to Dirac space 1 and gamma mu proportional to gamma mu. It's like a photon coupling. Those two are separated by the Lorentz scalar potential and the Lorentz vector potential. And the Lorentz scalar part is adding to the free mass, that one. And free cases, no potential, then sigma B mass is heavier than the cascade. But you can imagine two light quarks condensates, it decreases faster than the one light quark condensate. So effect, you can imagine from this composite, already you can imagine. If partial restoration of chiral symmetry happens, then this mass in some density, it reverses. But Lorentz scalar means experimentally they measure also energy together. So Lorentz repulsive potential must be taken into account. So that part also issue of discussion, Lorentz vector potential, how it changes. Okay. Really, from this conclusion is here. You can already guess the conclusion. Then, usually how this model is modeled, but how this model is constructed. This is a baryon and meson levels effective Lagrangian. This psi is baryon, octet baryon or charmed baryon and bottom baryon you can think about. This case for nuclear matter I'm considering, then nuclear matter case here, nuclear mass centers. And here is the so-called scalar part, Lorentz scalar part. This gamma mu part is Lorentz vector part. For first, about the nuclear matter cases and meson Lagrangian is here. But usually, Waleczka model are relativistic mean field theory. They start from the meson and nucleon or baryon level. it means here they can introduce scalar and vector potential, but not explicitly include the Quark degrees of freedom. And people usually agree baryons have substructure. Then, okay, nucleon level, nuclear matter baryon density and scalar density, you can calculate. But point is, here, scalar potential, we calculate using some relativistic confined Quark model. And vector potential as well. But the important thing is because of the Quark structure of baryon, this Lorentz scalar effective mass gets nonlinear dependence, nonlinear sigma dependence. Usual relativistic mean field model, they introduce higher order sigma to the cube force or omega to the cube force they introduce and different potential. But starting from Quark degrees of freedom, we don't have to do it. It's a rather simple model, but it's okay. Can explain a lot of things and less parameters. Important thing is Quark, light Quark, and meson coupling. Always you can think about coupling constant. You don't have to introduce many coupling constant because, okay. Then goes into the structure of baryon. This case is a bug model. This is okay if you have a better model, but this is simple, relativistic and confined Quark. Then to describe hadrons, we solve Dirac equation at the Quark level. This is light Quark. Light Quark is subject to have potential due to the sigma meson Lorentz scalar. Behind physics behind of this is light Quark condensate changes very faster than the other quarks. Then based on that approximation, sigma Lorentz scalar potential mean field gives influence to U Quark and D Quark, and U bar and D bar Quark. And the strange charm bottom Quark, it's the same. That is the approximation, very crude approximation. And using the solving this Dirac equation and mass formula, the bug model formula is this one, and calculate Lorentz scalar mass at the Hadron level or baryon level. Then how it goes? Okay, nucleon level. This sigma or sigma potential, Lorentz scalar potential, it enters baryon level, but this also enters here Quark. VQ sigma is like MQ star mass GQ. This sigma is the same potential. Then first solving, given not converged mean field starting from this one Dirac equation Quark level and calculate Quark wave function is modified and put into the mass formula of hadron and nucleon and go back into the this nucleon level and calculate, solving Dirac equation nucleon level and calculate baryon density, scalar density, and repeating to achieve this nuclear total energy per nucleon, and to get the nuclear matter saturation density always repeating self-consistently. Once if you achieve the saturation properties of the nuclear matter, it is, for example, nuclear matter density, binding energy of nuclear matter is 15.7 MeV, then coupling constant is fixed. Then after that, okay, here, Quark and sigma meson and omega and Quark. Coupling constants for light quarks are fixed because it's determined by the nuclear matter saturation property. So after that, big achievement, because any light quarks in any hadrons, when hadron is immersed in nuclear matter, those light quarks in any hadrons have the same coupling constant. And those hadrons' properties or mass or potential changes, but the same coupling constants. We don't have to change anything. Then very economized parameters are fixed. That is the main point. Main point to use the Quark model. Otherwise, you can introduce any different coupling constant for different hadrons, always, no systematics. Okay, then. Yes, only the talk a little bit related to the mass. Yes, I forgot this. It's somehow a dynamical mass or Lorentz scalar mass. This first. Yeah. Okay. Well,
What's the question?
No, I prepared but forgot. Sorry. So mass, you want to go to the mass, but then I myself a little bit. Here, hadron mass is calculated by the applied Quark model. That is a little bit different. So if you use different Quark model to describe such a model, this mass formula is different. Then, so
the mass comes from the kinetic energy,
but this is
and the back pressure.
Yes, it's a bug model. So if you suggest some different model which can treat easier, it is better. And in lattice calculation, if they can calculate some potential for Quark, this one, infinite density, then you can put and can calculate, I don't know, baryon mass in lattice QCD regime. And if you can have density dependence of baryon mass by lattice QCD, you can apply. That is also okay. Then put into the baryonic level Lagrangian, and you can calculate, such baryonic level Lagrangian solvent. You can calculate the properties of a nucleon or octet baryon. That is eventually a good thing. But this is only crude, but the first step. But already 10, 20 years. So I have been waiting other people. But relativistic harmonic oscillator models, they are successful, but in the end, they had to introduce sigma to the cube, sigma to the fourth, omega to the cube, omega to the fourth. They had to introduce again, starting from the Quark model, relativistic harmonic oscillator model, they had to introduce again potential at the meson level. Then it destroys everything. Because to fit the experimental hyperon and nuclear structure calculation, without such new potential, they cannot describe the properties of finite nuclei. Okay? Bug model's case, it was okay. Then mean field is calculated from the Lorentz scalar and Lorentz vector, and here enters nuclear matter. The nucleon mass, effective mass, is calculated from the Quark level. And if we are starting from point like a nucleon, here it becomes 1 and 1. This sigma dependence comes from the substructure of nucleon. And by this one, relativistic mean field formula, you can calculate the energy per nucleon and fitted the coupling constant determined. One subtle feature is, if I start the current Quark mass 5 MeV, coupling constants are different, sigma and omega. Also, 220 MeV, we applied also low meson, pi meson cases, 220 right from the Quark model, then coupling constants are different, and incompressibility is also different. Parameters are different. So depending on starting Quark mass, if you start from 330 MeV constituent Quark, also different nuclear matter properties you obtain. Okay. So anyway, starting from Quark structure, and you get the sigma dependence of effective mass, not 1. And here, this is an interesting point. Nucleon mass derivative in terms of sigma field, it is related to the ground state Quark wave function scalar charge. This is a little bit related to the Quark condensate. It means in this model also, not exactly Quark condensate, but scalar, psi bar q, psi q, this integrated one is related to the effective mass. And this wave function is obtained solving the same this background of sigma field. Then self-consistently they are influenced. And scalar charge of Quark. If this is a Quark condensate, this is a really dynamical symmetry breaking, and it's order parameter of chiral symmetry in finite density. Then, just I showed formula. Then this is the nuclear matter energy density. This is density and this energy. And one normal nuclear matter density is 15.7 MeV. This incompressibility is this curvature, this one. And this is nuclear mass, how it changes. This one. Already. Okay, so good. Then it's okay. This is not observable, but how change the Quark potential, 5 MeV in this case, and this and vector potential. And repeating again, light quarks, all the light quarks in any hadrons feel the same potential. That is the big.
Light quarks include strange?
No. Strange.
Just up and down.
Yes. Strange, yeah. Subtle, but strange now 100 MeV or something. Then we must introduce a phi meson. Then complex feature will appear. Then to show the difference, for example, 220 MeV cases right from Pion model, Pacheco and we did. This curvature is this one. This is 5 MeV. So increasing density, how energy density increases is different. Here, 60 MeV, this is scale, here 30 MeV. So curvature becomes different. So different nuclear matter properties are obtained depending on the starting Quark mass. But empirically, this 260 or 70. So it means right Quark mass 5 MeV starting is preferable. Nuclear mass also changes. Starting from heavier Quark mass, then decrease faster. That's why Waleczka model, they, without the structure, and if you think about 3 times of the 330 MeV, nuclear mass decreases very fast, unless they don't introduce sigma to the cube force, omega to the cube force potential. To avoid such a feature, they introduced. Okay, it's okay. Same. Then just a comparison, summary of different Quark mass starting and coupling differences. Okay. Then, okay, go. Yes. And one interesting feature is always I want to show. It's a scalar potential for different sectors. And the nucleon has 3 light quarks. Sigma, lambda hyperon, 2 light quarks. Cascade 1 hyperon. Cascade C, the sigma C, sigma, lambda B, lambda C is 2 light quarks. D meson and B meson, they have 1 light quark. Omega, low 2 light quarks. Then this is scalar potential amount, this 1, 2, 3, nearly proportional to the light quark number. That's usually people think it's natural, but okay. Demonstrated by numerically in the model, this is okay, good way. Otherwise, you can guess always coupling constant is proportional to the number of light quarks. Only that guess. This is a really model calculation to demonstrate. Then go to the interesting cases. So strange sector and charm sector and bottom sector and in vacuum input. Here, I don't mention about the strange and charm. Strange, we calculated also hypernuclear properties, but I don't. Sigma B, as I mentioned, mass is this amount particle data and also recent experiment. And the cascade of B, light quark strange bottom, is lighter. That was the first how people can, some model can explain reasonable or I don't know, lattice calculation they can reproduce or not. That is also one question. Vacuum.
Can you understand why sigma B, the radius, is larger than for the nucleus, say, or the others? Because I would expect that when the quark is heavy,
Yeah.
it will have less kinetic energy. So the radius should be smaller.
Yeah, radius, but bug radius. So I don't know, bug radius is not observable, but the mechanism is, I think so. But it's not physical things. I should.
You mean if you calculate the root mean square radius,
Yeah.
you will find that sigma B is smaller.
Can be, depending on how much the light quarks influence to give the. You must calculate psi bar psi and r square and the integral over light quark and two light quarks and B quark and calculate and one light quark strange B and sum over and you must count.
But I would expect them to be smaller than only light quarks.
That I didn't do. I want to do, but I didn't do. I haven't.
You know, once see the result.
No, this, okay. No, first mass, okay. Then, at nuclear matter density. Then, here, reverse happened because this much more influenced by the light quark condensate decrease or effective mass decrease. Okay, then here's other things. Okay, maybe it's not. This is bug frequency and bug radius, but it's not so much. This is for parameters to get the quark wave function. Using quark wave function, I must calculate something. I plan to, but many things to do always. Then the figure, here's it. Left-hand side is strange quark sector, hyperon, and right-hand charmed baryon sector. Starting from the vacuum mass, and the density increases, how effective mass decreases. It's the same feature because similar feature. For example, this is cascade of only one light quark, and sigma and lambda, two light quarks, nearly parallel, and nuclear. And the charm baryon case, starting mass is different. Here is cascade C, sigma C, and lambda C. Lambda C and sigma C is nearly the same. And similar thing, go to the, okay. Here's strange part and the bottom part. Because starting part is different. Cascade of B is lighter and sigma B is heavier. That's why here, crossing. But this curve is for lambda B and sigma B similar. Okay. Yep. Mass from starting from decrease. No, not zero. Already up to here model limitation. Then you must use some, you started NGL model or something, you must do that one. This model is limited. But still less small density this happened. But this is only Lorentz scalar, then this is the bug model parameter, so I can skip. It's not so much. Indeed, the wave function changed, everything changed, but okay. Bug radius changed also here. Bug radius. So light quark, if they have many light quarks, bug radius changes. Then one thing is we studied hypernucleus, sigma and lambda hypernucleus. Sigma hypernucleus doesn't exist except for helium-4. Then why it happened? it's usually sigma and lambda mixing or other mechanism. Then to calculate the energy levels, sigma and lambda, that difference must be included. They break SU3 symmetry. Then such vector potentials influence, if we should include the cascade B and sigma B cases. How it happens, then this one. Okay. If this model naively predicts the potential for sigma B and cascade B, that doesn't include sigma and lambda channel coupling in the strange sector, because lambda B and sigma B has much more big mass difference. So although I expect less channel coupling, but I calculate both two cases. If I include the same effect, lambda sigma effect of strange sector, if I include scalar potential plus vector potential, then here is sigma B, this upper part. This is probably relevant for experiment. And this one, this one is cascade B. Then they never cross each other. But this includes the repulsive stronger potential, the same as for lambda and sigma strange sector. But the model itself, naive way calculate here. This is okay, sigma B, and including vector potential, cascade B. Including vector potential, then here around normal nuclear matter density, energy levels, total energy, all nearly degenerate. Then still you can find some interesting phenomena. So production of sigma B and cascade B, it costs similar energy. So production rate of sigma B and cascade B would be similar, although this is zero temperature. Including temperature, but that is okay. One suggestion. Okay, that's okay. So main point was sigma B and cascade B, varying effective mass or Lorentz scalar potential, and also excitation energy, including vector potential. So using obtained wave functions in nuclear medium or symmetric nuclear matter, there are many things that can be done, but okay, electromagnetic form factors, weak interaction form factors, or I don't know, maybe pattern distributions. If I don't know so much detail how to calculate. If someone can calculate using bug model, I can provide the wave function. Heavy on collisions, but the reaction only elementary, simple reactions I did in the past. And other interesting applications, if you have some idea or if you want to calculate something, please ask me. I can give wave functions and data. Okay.
Okay. Thank you. We passed the time, but let's allow two short questions.
You understand what is happening, because you start with the nucleon, then you replace one light quark by a strange quark, then the mass decreases. You replace the strange quark by a charm quark, and the mass decreases.
Yes.
Now you replace the charm quark by the bottom quark, and then the mass increases. Why? Because
mass doesn't increase. What do you mean? Yeah.
You don't have any other dynamics there, right? There's no extra degree of freedom, only the mass. Why is it changing the behavior?
Light quarks dynamics is the same for, so
sure.
Always the same.
But you have a tendency as a function of the heavy quark mass, always decreases. When it gets to the bottom, it increases.
No increases. No, here is, okay. So all those baryons, light quarks, wave function follows this one. And heavy quark follows this Dirac equation. Then this formula decides everything.
Yeah, and what happens so strangely when you get to the bottom? that the tendency is reversed.
Not reversed.
Sure,
It's
but the bottom there gets larger.
what do you mean? Not this, okay? Sigma B and lambda B,
It's only
same.
the
same.
difference.
Yeah, same. This, okay. Cascade and cascade B is also similar. Yeah.
You should continue discussion in the coffee break. Any other question? Okay, let's thank the speaker again. The next speaker is João Pacheco B.C.
Okay.
And if he doesn't change the title, he'll talk about extraction of the electromagnetic form factors for spin 1 particles on the light front.
Okay. Sorry.
Hi. Okay. Hi. First of all, thanks for the organizer, especially Gastão, Bruno, giving the opportunity to speak here. And I put some collaborators here, Tobias Frederico from ITA, Bruno Berenice for the Sul University, Kazuo also speaker before, Gilberto Ramalho is chair, and Clayton is a former professor now in north of the country, Universidade Federal do Amapá, and Narcís PhD here, Georgia Buzak is PhD, my student, Romo Moita, Vakani is master student, Shang-Chi from North Carolina, US, Ahmed and Ali Paracha is former postdocs from Pakistan, Eduardo Rocha is the former postdoc from Colombia, Orlando Oliveira is professor at the University of Coimbra. I speak about Homer's with light front approach. That is, light front is very important to use for high energy physics or Hadron, but then you need some care. Why you need a light front? I give some motivation. I give for students almost the overview of light front. Then I go to specialize the whole meson. I calculate the plus component of the current. Then I have my model wave function. I explain a little bit angular condition, the problem with the prescriptions, the problem with the combination to eliminate the zero modes or part terms, and some conclusions. Well, why you use light front? Because it's the framework to describe Hadron bond states. And you have unambiguous pattern contents of the Hadron system, composite system.
The first statement is not true, right?
Huh?
The first statement is not true.
No, yeah, but it's work a little bit. And the representation of a composite system in quantum field theory is invariant under boosts. Light front is trivial, is not really true, I agree with Gastão. And after integration K-minus, you can obtain, K-minus is the energy in light front. You can obtain the wave function, some bets of amplitude. And the total Hamiltonian of the system is invariant with Lorentz transformation. That is more for students, quad vector, you need to write it this way, plus component, minus component, perpendicular, components, combine the time plus the 30 components. This way is the time, is the position. Also, the metrics in light front are different. The quadriproduct, you need to use this metric. Is different for the usual metric. And, for students, directly introduce this. I show you later. And you can relate it with the form momentum, P plus, P minus, P pep. And P plus is P0 plus P3, P0, P minus P0 minus P3, P pep is P1, P2. And the direct matrix, you can combine also gamma 0, gamma 3, gamma minus gamma 0 minus gamma 3, gamma pep is gamma 1, gamma 2. plus component of the current is the combination of the two, they are related with Dirac matrix in this way. And okay, then you have quasi moment for the product of quasi moment. P minus is light front energy. If you have the particle on shell, you have this condition. For bosons, Feynman propagator for bosons not have any modification compared to constant form. But for fermions, you have this term plus. This term, if P plus goes to 0, is a turbos. That is the root of the zero mode or the fluctuation of the vacuum in light front. For a student, you can take the Stanley Brodsky and Professor Paul Lipinski paper a long time ago, or Hinana writing, also in James Very book, 97, and a lot of books about that. Okay, then why you solve this? Many years ago, 97, I found some method I call dislocation Pauli method. If you have a Feynman amplitude and you need an integrating combine, then you just dislocate one pole position. Then you integrate. Then you have the plus component, the valence component, plus something else. This is zero modes or no valence component. Is this, for example, J plus, G plus for boson, no problem, but for G minus, you need to take care because you lost covariance. That is published many years ago. And also similar works by Shang Yan, Savik, and another one. Okay, now I go to spin 1. Spin 1, you have 3 covariant form factors. And you have the polarization is the more general formula you can calculate your electromagnetic current. Then I show this polarization here. You can choose any polarization you have. I show the bright frame because the calculation is more simple. And I calculate only G plus here. I have had a preliminary result for G minus, but not yet finished. And I need a model. No, I need a model for my Feynman amplitude. That is my Feynman amplitude. Correspond to the triangle diagram. I need this amplitude is divergent. I need to regulate. And also, I not show you. I have some model, some equation to solve, and then I obtain the vertex model to bond states, quark, anti-quark. And after integrating K minus, here is exactly the Feynman parameter. I obtain this mass square function. M dot is the free mass operator if you have a Hamiltonian free. And is the regulator coming from the regulator function, okay? And after that, I obtain the wave function. It's quite quite complicated. It's already published some years ago, and also. Okay, what is the problem? The problem is you have 4 matrix elements in instant form, and you have 9 matrix elements, but after parity and some rotation symmetry, you have only these matrix elements. Also for light front, you have 4 matrix elements. You can go Cartesian base to light front base with a Melo rotation. It's like a Wiedner rotation for the students. And you can write the light front bases in terms of Cartesian base. This way. Oh, sorry. Yeah. Then you have this condition. It's discovered a long time ago by Inagati, Leonid Frankfurt, Kodayaku, Stickman. You have this condition you need to satisfy. In the instant form, it's 0. If you integrate AA, zeta is 0. But in light front, it's not 0. Then you have the violation. This is a rotation violation, parity violation. That is very important because it's the turbos, because you have some ambiguity to choice matrix elements here. Why? Because you have only 3 form factors, charge, magnetic, or dipole. But you have 4 matrix elements. Then the prescription born here. Frederic Frankfurt Stickman have an prescription, Inagati, Kodak have a lot, Koster, Schunk, Kester, Polizou have another, Brodsky, Hiller, another, Vladimir Karmanov, another. Depending which element of matrix you eliminate with your angular condition equation. And in Agache, eliminate exactly 0-0 polarization. That is important. 0-0. Take attention to this. Okay? And 0-0 is here for Koster, Keister, Polyzul, Chung. 0-0 is here. You see, it's important. And also in Brodsky-Hiller, 0-0 is here, here. And Frederick Frankfurt-Stigma only charge form factors are different. Another is the same for Chung and Polyzul. And Karmanov also 0-0 is here. That is important for all form factors. And why you need to recuperate the covariance? You need to add not just wave valence, but also the sparse terms, no valence components in your Feynman amplitude. Then you can student by parts this vertex I have. I studied by parts, for example, for gamma nu in the vertex. Then I can separate exactly the dependence in K-minus, which it is this common factor for all amplitudes. No, if it is pores appear, no part term contribution if m less n. Okay, that is detail. I arrive exactly in this, thank you. I exactly arrive in this relationship between the trace and the level of the trace. Okay, it is a common factor. It's proportional to the momentum. You see, it's proportional to the momentum. And also, AA is a proportional K-minus, but is a proof for the Pion in 99. This matrix element for the 0 mode gives 0 for plus component of the current. Okay, then I calculate in the Cartesian basis. You see, for all components is different of 0. It's the 0 modes. All components different to 0. I use the method I showed before, Pauli dislocation method. And for II is 0. And I put in the light front basis. Only zeta 0-0 polarization is not 0. And proportional zeta zeta. You see? If you remember, all prescription use this 0-0. Then broken the convariance. In Agache not use this. By feeling, I don't know why. She eliminates exactly the matrix element not have any problem, any broken of covariance. In Agache eliminate 0-0. Then in Agache have this form factor I showed before. And if you put this contribution 0 mode, you obtain for all form factor 0, because in Agache not have any contribution 0 mode. And I go to gamma mu and derivative is quite technical, but important thing is that for II you not have 0 modes, but for another ones you have. But if you can again use the Pauli dislocation method, you have this 0 modes proportional to theta plus, for example, ordering of theta, delta plus, sorry, and the delta plus here. Then you got this delta goes to 0, and the 0 mode not appear anymore, only for 0-0 components, okay? And, okay, that is no 0 mode per contribution within Agache prescription. That is published, also TZ appear again. And then another way to see the broken of the covariance is you make the difference between the in Agache and another prescription. If you see, for example, Brodsky-Hiller in Agache, you see all is proportional delta, but delta is the angular condition, also proportional to the moment transfer. If the angular condition is satisfied, this difference is 0. No? If it is the equation satisfied, the difference is 0. Also for Koster Polyzul minus in Agache for all momentums. Also for Karmanov, but magnetic form factor for Karmanov in Agache is the same, and then they give 0. But you see, it's very interesting because all difference is proportional to angular condition equation. Also Frankfurt Frederick Stigma. And then you can use this trace I showed you before, and you arrive at these nice equations that I put VIP, because it's really nice. Use these equations to calculate the matrix elements. Then you can eliminate, with this equation, you can eliminate the zero modes. Then you have put in the Coste-Kite Polyzool, for example, you obtain the exact charge form factor in Agate-Rev, magnetic, and quadrupolar. Also Frankfurt-Stickman, also for Brodsky-Hiller, you obtain exactly the same in Agate-Rev. Also Karmanov, Vladimir Karmanov. All prescription in this way because I use to include the zero modes and eliminate the broken of divergences. Then you have this, the angular condition here. Is give zero in instant form, covariant. Without zero modes is here. With zero modes is give zero. Is broken a lot. You see? Broken a lot. Yeah, 20 GV square. Okay, I can calculate also the K constant. The K constant, here you not have the first part of the trace, you not have minus dependence, but here you have. But because the structure of my vertex, my model, this cancel out and no zero modes. And you can calculate the observable charge, magnetic moment for the Romeson, quadrupole, also the radius, electromagnetic radius. And you see the difference, I show you for the charge form factors between Inagati and another one. All broken. After you include zero modes, I'll give zero here, not the difference. And here you see the traced, dotted, no? Dotted is without zero modes. Solid line, you cannot distinguish with zero modes for all prescriptions. All prescriptions give the same result. Also, the zero of the form factor change after you include the zero modes, give the same results. Also, for the magnet, the difference, and after zero modes, no difference at all. Also, no, aqui magnetic again, the difference and the magnetic. And the quadrupole, they broken a lot for some prescription. For example, Inagati less Kamanov, Kamanov less Inagati, broken a lot. And also the quadrupole form factor. But after include zero modes, I'll give the same results. And this compare light font models with another model. For example, Gauss, long time ago, light font, QCD some rules, point form. For students, point form in the paper of Dirk, 49, have another form of dynamics. You can use point form. Choi, Melikov, light font, QCD some rules, Schwinger Dyson, relative quantum mechanics, light font constraint Quark model, Schwinger Dyson, light font. Then you compare. And also Lattice. It's not so far the light font results. Then is the zero of position of charge form factor. Is related to 5 times square root of the Romeson. Then you have a comparison with the Schwinger Dyson, another light font model. Is the previous table, no? Choi, Xuangji and Choi, Ben Barker. Tomasi is quite, she used some fix that fit the some phenomenological model. And also the magnetic moment for the Romeson, and compare also with Lattice here, or here, Lattice. Okay, that is my remarks. You can use light font, no problem, but you need to take care about broken some symmetries and almost problematic minus integration integrals. Also solve integral equations or just integrate. But in present work, I calculate only J plus, but I work in minus components and prep components. Then the light font, you can take information about correlation quark and quark. Distribution amplitude, I have already calculated with my colleague Kazuo and this Tiaka Ahmed for the Pion and the Kaon in the medium and the vacuum. I can calculate Romeson decay, for decay in Pion, deuterium. Someone from China already used this model, calculate the deuterium, but then the guys introduced also D-waves. And this model, also, like Kazuo mentioned before, is applied for the Pion, and it is here applied for the Johansson. Okay, thank you very much for your attention.
Okay, let's thank the speaker. We have 10 minutes for questions.
Yeah.
Wait.
Thanks. No, I just wanted to understand. I mean, you showed the propagator in the beginning and said that this is
the
your
Feynman
model.
propagator.
Yeah.
The first one.
Like, I guess this is, this
You can
was my,
continue. I just take care.
yeah,
Sorry, too much.
it's okay.
Yeah, here.
No, the next one where you talked about there has to be a model.
Ah,
Yeah,
here.
yeah, that one.
Yeah. The
I
electromagnetic
guess
current.
this is sort of the closest that I could think of why you call this thing a Rho meson rather than a generic vector particle.
Oh, it's
Like, why is it a
you
Rho
can
meson?
It's a generic if you want. It's generic. Only thing is the model you need to put here, no? The vertex. It's a very generic Feynman amplitude triangle diagram.
There was a Feynman diagram on the
Yeah,
next
sure.
slide, right?
The Feynman diagram. It is
Yeah.
I think it's
Which
maybe
incorporates-
put exactly. I put my Feynman diagram. Yeah, here. You see, then the vertex, you enter here, is a gamma mu here because it's the photon, gamma mu plus, minus, or paired. Then the lambda or gamma
So
the vertex.
the reason it's a Rho meson
Yes.
is that it's a vector particle that interacts with a
The photon.
photon via
Yeah.
triangle.
Yes, exactly.
Okay, that's what, I mean, for
Then,
example,
after-
a Z would
because-
not do that. Yeah.
But in light front,
Okay.
if you calculate only times the gamma, you lost the symmetry. You lost this zero mode contribution. Ben Barker applied for W. Quite similar to this Ben Barker and Chong-Ji apply for W, quite similar to this model for W.
Is there can you generalize this to like number of flavors and number of colors which
sure.
are different?
Yeah, people apply for another thing.
Just,
I apply for K, or I don't know, but 30 minutes only.
I see.
I have
see.
another works.
Thanks.
Yeah, right. Also deuteron.
More questions?
Nucleon, deuteron.
My question is still about your model. I didn't understand what's the particularity of your model.
What is?
What's the particularity? What's new in your model? I didn't understand this.
No, the particular thing is not the model. Not the model. Is the way you recover the covariance. The way is not so clear. Brodsky, Professor Brodsky, no? 20 years ago, if you use plus component bright frame, the covariance is fine. It's not fine. You see the figures, no? It's not fine. You see the figures. I put the full, it's the full form factor. But I can put the gamma mu derivative. You see? The Brodsky. Brodsky is here. You see? This is covariant calculation compared with light front. After include zero mode. In a graph not have any zero mode. In a graph give exactly the covariant calculation. Okay? Instant form basis. Covariant, I say instant form, not light front basis.
Please explain vertex.
Sorry?
Vertex.
Vertex.
Yeah. What do I do? Vertex.
The Brodsky. Romero, I use this one. Sorry. My vertex is this one, and I have this wave function.
My guess
No,
is
no, yeah.
his question is what kind of characteristic
You can use another one. For example, Chong-Ji use Chong-Ji, Brodsky also use. I use this wave function. Chong-Ji, Brodsky use Gaussian wave function. That is your question. No, is your question. That is the model is here.
That is good or
Yeah. It's good. It's good. It's my model. It's good question. No, I don't know. You can compare the table. Sorry, I'm joking. Because you're joking, I'm joking, yeah? You can compare the table. I think you need to take a look at the table. It's not so far another calculation, more sophisticated string dice or LATS. You can compare. That is the model in this moment. Compare with the particle data group for the decay const. Compare with the magnetic moment called the pole and the radius with another model. You see, the problem is home meson not have data. But I have also another work I made with Chongji and Tobias, analyze Baba experiment to see the perturbative, asymptotic perturbative QCD, the physical letters B. And I show something else with experimental data from Baba.
More questions?
Yeah. Sorry, Fábio.
Is there any particular reason to exist only two, your and the other, estimations for F row?
No, because the guys don't calculate. Only the guys not calculate. In the papers, I don't know, I not solve Schwinger-Dicke equation, put a number here. Or maybe I need to send emails for the guy. But people, in general, people calculate form factor and calculate this magnetic moment, quadrupole, and the radius.
More questions? Okay, I have a question of my own. Are there any lattice QCD data for finite Q square? These are just static values, right? Oh, in terms of dependency in Q square.
Oh yeah, in terms of
form factors, for instance. No?
This is a physical home meson that another is not physical, it's just
that's the
fit,
zero, right?
That is the fit, yeah. Fact.
Okay.
Ma is here, I don't know, Melo is here. Robert is here, but not Craig Robert, I got Robert. Salmé, Diane like front, Shoji is here. I don't know, Tomás is here. Yeah, it's the zero form factor. The zero charge form factor. The form factors change with the home meson mass. If it not include the zero modes, also the position of the zero change. I think it's here. Oh, sorry. Yeah. Zero, no? Zero, yeah. If not include zero mode, you see the position of the zero change.
Okay, let's some questions for the coffee break. Let's thank the speaker again.
Okay.
Should we return at 4?
Oh, vocês não conseguiram?
No, let's turn at 4:30. I said 4, I was wrong. I cannot use the monitor and the watch at the same time. Let's turn at 4:30. Coffee break. Let's return at 4:30. Precisa de ajuda? Do you need help? Or just replace the Linux or Windows? Sometimes it's tricky. You need a mouse or not? Then you have to